Here's a few ideas about electrolytic cells. We're going to talk about electrolysis and electroplating here. And in a sense, this is the opposite of the electrochemical or galvanic cell. There are two types of electrochemistry. The electrochemical cell, or galvanic cell, features the spontaneous, we should say favored, flow of electrons from the anode through a meter or a motor or a light bulb to the cathode. Energy is produced by the cell and used to do work. The electrolytic cell is in a sense the opposite. You force a flow of electrons to go from the anode to the cathode by hooking up an external battery or a generator or an alternator like you have in your automobile. Energy is used by the electrochemical cell to make high energy elements and maybe even compounds. The free energy considerations that are involved, I've put the two types here on the page, and I want you to think about it and decide what is the sign, SIGN, of delta G for each type of cell. The electrochemical cell must have a negative delta G because the flow of electrons is favored. The electrolytic cell must have a positive delta G because it won't happen by itself without forcing the electrons through the circuit. Let's talk about something familiar to most people, the lead-acid battery that is in most conventional cars. The charged battery has lead in contact with sulfuric acid inside the battery. The sulfuric acid is the electrolytic solution that you have. Lead then is oxidized at this anode to form lead 2 sulfate, and the oxidation of course generates electrons. Lead dioxide coats the other electrode. It is also in contact with the sulfuric acid electrolyte. Lead dioxide then is reduced from the +4 lead to +2 lead, as you find in lead 2 sulfate, by adding electrons. When the battery is completely discharged, then you have lead sulfate coating both electrodes in contact with depleted sulfuric acid, and it will no longer generate a current. How do you recharge a discharged battery? This of course is critical because you need that battery to last for even years. Lead sulfate is coating both electrodes. You've got depleted sulfuric acid around it. You've got to force electrons now to go in the opposite direction. The automobile generator is hooked up to the battery, and it does force electrons to go in the opposite direction. Lead sulfate then is being oxidized to lead dioxide or lead 4 oxide, +2 to +4 oxidation state on the lead, and lead 2 sulfate is reduced to elemental lead at the cathode. Now the lead and lead 4 oxide are restored at their proper electrodes in contact with regenerated sulfuric acid, and they're now able to start your car the next time you need some power. In summary, discharging involves producing electrons from the lead. Here is the balanced half reaction. And discharging, of course, also involves reducing the lead 4 oxide to lead 2 sulfate. Charging restores the original situation, lead on one electrode, lead 4 oxide on the other. Batteries die when enough lead sulfate falls off one or both electrodes so that the battery can no longer hold a charge in the electrolysis cycle. The circuit then would be broken. Now let's look at some electrolysis reactions to develop some experience that helps us understand the theory and problems involved. And there are a number of YouTube videos that you can look at for that purpose. When a voltage is applied to an ionic solution, which ions react and what is produced? Because we usually have multiple ions present. And then does the amount released depend on the number of coulombs added? And I'll tell you the answer to that is yes. So what reaction happens when you apply a voltage to a couple of electrodes dipped into ionic solutions? If the voltage is supplied to a mixture of cations, which one of the cations will plate out as a metal? Well, since this is the cause is reduction, let's look at the reduction potentials on the table. And so if we ask the question, if we mix silver plus ions, copper 2 plus and zinc 2 plus, and apply a voltage to those electrodes, which one of these will preferentially plate out? Now the more positive voltage has a more negative delta G. Thus, silver ions would plate out in preference to copper ions, and copper ions would plate out before zinc. Silver would come out first. Once the silver has been reacted, you can then plate out the copper. Now let's look at electrolyzing brine. That's concentrated sodium chloride solution. At the cathode, we're providing electrons for a reduction. Now we have water present, and water can be reduced to hydrogen gas, with hydroxide also provided. At the anode, oxidation occurs, electrons are taken away, and from what? Well, we have chloride present, and if you look at the reduction potentials, you see that for an oxidation, the chloride would be oxidized before the oxygen and the hydroxide. So what valuable stuff are we producing? We're getting hydrogen gas. We're getting sodium hydroxide because we're electrolyzing sodium chloride, and we're getting hydroxide ions. And we're also producing chlorine gas. All three of these are valuable. This commercial process is frequently used to get all three of these products. Let's think about diluted sulfuric acid and electrolyzing it. Well, at the cathode, we're providing electrons for a reduction, and again, water is present, and we can produce hydrogen ions. At the anode, we have oxidation occurring, electrons are being taken away, and here we have no chloride available anymore, so we're going to be electrolyzing the water in the other direction, and we're going to get oxygen gas. What valuable stuff is produced? Hydrogen gas and oxygen gas. Both can be sold. The trouble is, oxygen is more cheaply produced by using a very good refrigerator to liquefy air and then separate the components like carbon dioxide, nitrogen, and oxygen from the liquid air. We can now also electrolyze molten sodium chloride in what's called a Downs cell. Now this is plain old table salt that has been melted at 1074 Kelvin. So we're up in the 800 degrees Celsius range. It has to be done in a very stout metal container. The chlorine gas that comes off has to be gathered, and the sodium metal that comes off as a liquid, and that of course has to be collected. And all of this has to be done in the absence of air, because the air would react with the molten sodium. Here's the anode oxidation. Chlorine gas is produced from the chlorides, and reduction at the cathode. Since there's no water present, the sodium ions can be reduced to sodium metal, which would be a liquid at that temperature. You can use the same process to produce potassium metal, lithium metal, and the like. Electroplating is another commercial use for electrolysis. If we apply a voltage to silver ions, we can plate out silver. Should we put the item to be placed at the cathode or the anode? Think about that. In any kind of electrorefining like this, if we have an impure metal, we're going to put it at the anode because that's going to lose atoms, and the pure metal will appear at the cathode where reduction is occurring. Alright, we can also predict the amount of product given or taken away at any electrode. Current times time, we learned from physics, is coulombs of charge. Coulombs times the ratio 1 mole of electrons per 96,485 coulombs gives us the number of moles of electrons. And moles of product, of course, would be equal to the moles of the electrons times the stoichiometric ratio. So if we were doing copper 2+, we would have to consider that 2 electrons per mole of copper. Grams of product, then, would be equal to the moles of product times the molar mass of the metal being produced, or chlorine gas, or whatever it is you're producing. So the question, how much silver could we plate out with a 12 amp current running 3.5 hours using the prior slides' formulas? Go ahead and turn this off and then come back to it and check your answer. Here's your formulas that we received from the other page. Coulombs, we multiply the 12 amps by 3.5 hours times 3,600 seconds per hour. We then take the coulombs, divide by 96,485 coulombs per mole to get 1.57 moles of electrons. We then take the 1.57 moles of electrons, and we know that 1 mole of silver is going to need 1 mole of electrons, so that ratio is 1 to 1. And finally, the mass of silver is 1.57 moles times the 107.9 grams per mole. 169 grams of silver is produced. And that's a reasonable answer for the 12 amp current at 3.5 hours.